So, let's see here. All right. Let's see if we can connect to the room system in Valentine today. Hey, we connected to the room system. Is anybody in there? I can see a big picture of my head. Doesn't look like anybody's in there. Let's send out some emails. Let's see. Let's see. Is it Jacob that's not here in class? Neither of you are Jacob. So it's Jacob. That's what I thought. We'll say that's right. Okay. I don't know if they're going to show up there or not, but we'll just assume that that's fine to leave on like that, and we'll move on with life here. Actually, we go back to this thing. Back to meeting. Share screen, just in case they're interested. We're still going to see a big picture of my noggin. All right. So we finished up in section 4.4 last time. We didn't really get on to any of these last sections and all. And like I said, these last sections 4, 5, 4, 6, and 4, 7. We already talked about the 4 basic forces. But 4, 5, 4, 6, and 4, 7 are more just examples. Lots of different ways that you can use Newton's law. So what we're going to do is we're going to go through a bunch of these examples and just kind of take a look at them and see how they go. And then we'll ask you if you have any questions. I feel like putting my feet up today. I always feel like that actually. So let's go ahead and do this. Section 4.5, normal forces, tension force is another example of forces. We actually did kind of cover part of this when we did this skiing problem, right? Now this one I want to take a little closer look at it. I went rather fast through it, rather quickly through it last time. But this is a problem where we do something that we call rotation of axes. Normally our axes are X on the horizontal and Y on the vertical. But in this case, because most of our forces are either perpendicular or parallel to this slope here, and also the velocity and acceleration are going to be parallel to this slope, it makes sense to rotate our axes so that they're in line with the parallel, parallel to that slope and perpendicular to that slope. The reason for this is really simple. It just makes the math easier. If we don't rotate the axes, you can still do the work, but then you're going to have to convert this frictional force into components, one in the horizontal, one in the vertical. And the normal force will have to be converted into components, a vertical component and a horizontal component. So that's two forces that you'll have to work with the components of, instead of just one. If you rotate the axes, then these two forces are perpendicular to each other and they're pointing in the directions of the axes. So you don't have to calculate any components, you have to deal with them that way. And only the weight force is not in one of these two directions. Only the weight force has to be broken into components. It doesn't mean it's not confusing for people. It certainly is confusing, but it's certainly simpler mathematically to do this. And anytime we can make the math simpler, it's a good thing. Physics is hard enough. So when we do this rotation of our axes, then we get this triangle of forces that, this perpendicular weight force and this parallel weight force, so that when you add them together, equal the total weight of the skier here. So the total weight of the skier is this force. The frictional force points always opposite the direction of motion or the impending motion. And then the normal force is always perpendicular to the surface contact. So that one's perpendicular there. Here's your free body diagram, and then we break these two forces into two forces that add up to equal that total weight force. One of the things that people often do incorrectly here is set up these components incorrectly. Sometimes they want to extend this one all the way down here and all the way here and make the right angle here. But that's not correct, because then this bottom force is not pointing in the direction of the parallel axis, right? We want one force in one of these components to be pointing in this direction, and the other one to be pointing in this direction parallel to the surface. So that's the parallel one, that's the perpendicular one. So you have to do those correctly. And if you have an extreme enough triangle, it's pretty obvious to see where that 25 degrees goes. That's the smallest angle in this triangle. This is obviously the smallest angle in this triangle. Even if this angle is like 45 degrees or 40 degrees, well, if it's 45, it makes it really easy, but if it's like 40 degrees, just make the triangle weird. Just make it extreme, because how you draw the triangle is not going to affect your math. Draw it extreme so that you can see where this is going to be, because many people, when they see this problem, they think, oh, the parallel axis, that's kind of like the x-axis, and the x-axis is always the cosine. Because when we've done physics so far in the past chapter or two, it's all, that one that goes in the x direction, we've always used cosine. But in this case, it is not, because the 25 degree angle is up here, and this is the one that goes in that parallel direction, which some people associate with the x-axis. It's not necessarily, we're just calling it the parallel axis. But this one here is opposite that 25 degree angle. And the opposite angle in a right triangle always coincides with the sine function. So this ends up being the long side of the triangle, or the weight of the skier, times the sine of the angle 25 degrees. And this one over here ends up being the weight times the cosine of 25 degrees. And you see that right here. The parallel one is the sine, W times sine of 25 degrees. So you take the weight of the skier is just the mass of the skier times the gravitational acceleration. And remember again that that's just Newton's second law, mass times acceleration. But because of the angle that it's at, it's the sine of 25 degrees. And then the other one, which is the perpendicular one, this one right here, the longer one, is right next to the 25 degrees. So that one becomes the cosine, mg cosine 25 degrees. Once again, we've reached this is, we're in the third week of this class, third week of this class, right? We're in the third week of this class, and we've probably hit 5 points where students will come to me and say, I'm just not getting it. I'm not going to pass this class. Don't freak out. You'll learn this. You'll learn this stuff. We'll do more and more of this trigonometry stuff in the homework and in class, and you'll learn it. You'll get it. It doesn't take long before you're starting to understand things if they're not coming to you right away. And if you are struggling with them, make sure you tell me. Ask questions, come in and talk to me, send me an email, whatever you need to do. Phone call. And like I said, I try to check those every day, at least a few times a day. So. The only reason I haven't answered any emails today is because I had to do my budget today. And I had this $200 bill in my budget for my physics budget, and I had no idea where it was from. Figured out where it's from, now I just got to find the receipt. Can't find the receipt. Anyway, so then what we need to do is we need to apply Newton's second law in each dimension. Whenever you're in multiple dimensions, you have to do everything in every dimension, just like we did with kinematics in every dimension. In this one, we have to apply Newton's second law in every dimension. That means that the total forces, all the forces in the parallel direction, have to equal the mass times the acceleration in the parallel direction, right? And that's what they're doing here. So the total forces, which is the net forces, and they've solved this for the acceleration because they want to know the acceleration. So the acceleration is going to equal the total number of all the forces added together in the parallel direction divided by the mass. In the parallel direction, two forces. This is the parallel direction. Sorry, one force. No, two forces. There's the friction force this way, and then there's this W parallel component of the weight force. So this force and this force have to be added together. One of them is positive. The friction is positive because it's pointing in the positive parallel direction. And the weight force is negative because it's pointing in the negative parallel direction. So in the end, we have to calculate these two forces. They're going to calculate, let's see, is there a part, oh, so in part A there's no friction, right? So in part A there's no friction, so there's only one force. It's just the weight parallel force. Forgot about that. So the weight parallel force is the only force in the parallel direction in part A. So it's just mg sine 25 degrees. Now in this case they've actually shown this to be positive because all we're doing here is we're just trying to calculate the magnitude of the force. Technically this should be negative because it is pointing in that negative direction. It is pointing down. When we add them together we'll take that into account. But so we have mg sine 25 over m, and if it turns out that the masses cancel, we just get g times the sine 25 degrees for our acceleration of the skier down the slope. You're just taking a part of the gravitational acceleration, which makes sense. In this case, it gives us a little bit less than half the gravitational acceleration. Now what happens if we include the friction? That means that the net force in the parallel direction has to include the weight, the parallel part of the weight, and the friction. And here they do weight parallel minus friction. Again, I think this is a mistake for them to do it this way, but what they're trying to do here is they're just trying to calculate the magnitude of the force, they're not necessarily trying to figure out the direction yet since they know the direction. If I was doing this, I would actually write this as friction minus weight, because up here the friction is actually pointing in the positive parallel direction, whereas the weight is pointing in the negative parallel direction. It gives you the same number, it's just a difference of sign. Their way just tells you the magnitude, my way will tell you the magnitude and the direction. But in any case, this is the way they do it. So you take that original answer from part A, mg sine 25 degrees for the parallel force, which is the weight, part of the weight that's pointing in the parallel direction. And you subtract off the friction, and you get the total net force acting on the skier in the parallel direction, divided by the mass of the skier. Again, the masses cancel, and you get this little formula. You plug in the numbers, and you get an acceleration of 3.39 meters per second. Now, does this make sense? Compared to part A, does part B make sense? We have a nodding head. Why do you think it makes sense? Yeah, well, because we just took the difference between friction and weight. We did add the forces together. One of them was a negative compared to the other, so we added them together, which results in subtracting them. And so we got less of an acceleration, which we would expect. If you have a force that is in the opposite direction of the weight that's pulling you down the hill, then that, in this case, the friction, if you have a force that's opposing your down the hill movement, it's going to impede it. It's going to slow you down. And so the acceleration is not as much. Up here it's 4.41 meters per second. Down here it's 3.39 meters per second. Makes sense. Pretty simple stuff. Well, not necessarily that simple in the way we do all the math, but understanding it, I think, is not that hard. So here they just do a little demonstration of how you resolve weight on an inclined plane into components, and that's fine. Essentially, if you have the angle of the incline, then the parallel weight component will be W sine theta, and the perpendicular one will be W cosine theta, and the W, of course, is mg. I don't like to generalize things like that. They do it anyway, but eventually I'll rewrite this book to fit my own personality a little bit better. I haven't had time to do it, but eventually. So now we're going to move on to a new kind of force, well, a new manifestation of force, which is what we call a tension force. If you have force exerting itself through a material, so in many ways, you can do this in many ways. You can pull on a chain, you can hang something from a string, you can have a bridge that has towers and then trusses in between, and all those things are the forces of the cars going over the bridge actually exert forces. My favorite bridge, since I'm from San Francisco, is of course the Golden Gate Bridge, right? So on the Golden Gate Bridge, let's see a nice sideways picture of it. Here's a good one. There we go. So on the Golden Gate Bridge, you have many things that are acting in this way. The cars and the people. Did you know you can walk across the Golden Gate Bridge? If you're ever there, you should do it. You should walk across. It's really cool. See this stuff right here? That's actually netting. And there's netting all along here too, because it used to be that the sidewalk on the side was just there, and there was a gap between the sidewalk and the roadway that just went all the way down 300, 400 feet to the water. And it was a gap big enough that you could actually get in, you could actually slip into it. And a kid fell through it. And I think the first time a kid fell through it, they died because they fell all the way in the water. But many people, of course, jumped off the bridge. Many people have done that just to kill themselves. But a kid fell through it recently while the netting was there, and it caught them. But I walked across it before they put the netting there. It was kind of exciting. But anyway, it's definitely worth doing. For a long time, it was the longest suspension bridge in the world. But what we're talking about here is force, right? So here we have, on this part here, you have all these triangles. These are called trusses. And there are these triangles that are riveted together, these big steel triangles that are riveted together, and you can see them down here too. And what those are designed to do is take the weight of the cars and the weight of the bridge itself. You know, the bridge itself has weight, and to transfer that weight into lateral forces that move this way instead of this way, right? And you can see there's a bend in the bridge. That's on purpose. This bow in the bridge also helps to transfer forces downward, weight forces, into sideways forces, so that that weight can be pushed off to the sides, ends of the bridge. But more importantly, they're actually, what they really do well in this bridge is they transfer them to points right underneath all these points on these triangles are cables going up to these big cables. So these cables right here are like 8 or 10 feet in diameter or something. They're huge. And these other ones coming down here are, I don't know, half a foot, maybe 6 inches or something. They're huge also. Not quite as big, but they're still big. And the forces that are being translated sideways here, they actually all kind of meet up at these points. That's where all those forces kind of end up. And then these cables hold up those forces. And then these cables hold up those forces. And all the forces, this cable transfers it this way, and then this cable transfers the force this way, and all the force hangs essentially on the top of that tower. All the forces from this bridge, from the weight of the bridge, all the people on the bridge, all the cars on the bridge, they all those forces act down on these two parts of this tower right here, and these two parts of this tower right here. All that stuff is designed to transport those forces, to move them, to change their directions, so that they all get put right on top of there. It's a lot of force, in case you're wondering. In a very simple way, we can study this in a very simple way by thinking about this very simple example where a person is holding a rope, and the rope is transferring force from the weight hanging on the end of this rope through the rope to the hand. So the weight of the block here is pulling down, and because it's connected to the rope is pulling up on the block, right? So gravity's pulling down, and the rope is pulling up, and people think, well, that's because of Newton's third law, right? Equal and opposite. No, this is not. These two forces are acting on the same object, right? Remember in Newton's third laws, it's always different forces acting on different objects, right? It's the earth pulling on you while you pull on the earth. Even though the earth can't really feel it very much, you do pull the earth upward when you stand where you stand. Where we're standing here, we're pulling the earth this way. But it never really does anything because we're so tiny, we pull very, very little. The amount of gravity that we have because of our mass is very, very tiny. And there's also people in Australia pulling it the other way, so it all cancels out. Right? Anyway, so this mass has two forces pulling on it. The weight, that gravity is pulling it downward, giving it weight, and then the tension of the rope is pulling it upward. But why is there tension of the rope? Because at the other end of the rope, that force has been transferred by my hand. My hand is pulling upward on the rope on the other side. Right? So I'm pulling upward on the rope, and that means that the rope is pulling downward on my hand, which means this end of the rope can pull upward on this mass, which means that the weight here is causing it all to happen. Right? So all these forces going on inside this system. And you really could say, well, if this is my system, then my free body diagram is the weight down and the tension on the rope up. But I could also say the whole thing is my system and the force from my hand is up. So I'd erase tension here, but force from hand is up and weight is down, and these two tensions just cancel out because they're internal forces to the system. And tensions on a single rope or chain or something always cancel each other out unless there's something else pushing or pulling somewhere in the middle. In this case, the equation, the net force looks like tension minus weight. Tension is up, weight is down. And if this thing isn't accelerating, then the net force is going to equal zero, right? Because force equals mass times acceleration. If acceleration is zero, then the sum of all the forces just equals zero. If that's the case, then it makes it really easy to solve. This equation is easy to solve. That means the tension is equal to the weight. The tension in a rope that's holding somebody still, or maybe moving them at a constant velocity, is just a constant tension. Tension, it's equal to the weight of the object it's moving. If it's accelerating something, there's going to be more tension on the rope. But if it's not, it's just constant tension. So here are some examples of other things that we have tension in our muscles. So if you want to feel this, the weight of your forearm for an average human is about 10 pounds. The weight of your forearm has to be held up essentially by one tendon in your arm. You know what tendon it is? If you're just holding your arm like this, you can actually tell by feeling around in the tendon and feeling for one that's got a lot of tension in it. Go around and do it. A lot of people hate to do this, but do this really quick. If you reach into your elbow, try to relax your muscles, but just hold your arm like this. And reach in here and feel for something that's super tight. Can you feel that tendon right there? It has over 100 pounds of force on it from this 10-pound arm that's holding up. Right? And you can feel that's a lot of tension. That thing is super tight. And when people break that tendon, it's really bad news. If that tendon gets ripped or torn or broken in any way, it'll literally just, the whole muscle will just go up into the arm, and you have to like go up and fish it out, use muscle relaxant. It's bad news. But there are other places in your body, like the Achilles is famous for its tension, right? If that one pops, bad news. But your body's just full of these. In fact, your back has probably the most, your back has the most tension in it because of the angles. We're going to learn more about this in another chapter, but the angles of the muscles in the back are so extreme. This is why most people have back pain, not because of misaligned bones or anything else. In fact, that has the spine. A lot of chiropractors love to say that the spine is the reason that you have back pain. It's not. You can bend your spine literally in half and have no damage to the spine, and your spine feels no pain. Your spine really doesn't have any feeling in it. It has a lot of nerves, but they're not nerves for feeling things. The spine is extremely flexible, and it doesn't care if it's bent. You can bend it and tie it in knots. The problem with back pain is all muscles and tendons and the other things, the ligaments. Those things get pain in them because of all the tension in those muscles. So if you're not exercising your back regularly, and you're not staying in shape, so that your back can do what it needs to do every day, eventually those tendons will start to stretch. They'll start to get strained. They'll get overworked when you do something, when you haven't done anything in a while, and you go lift boxes for your friend when they're moving their house. It starts to do damage, and then when the ligaments start stretching and they start getting weak, then things get stuck in between the bones, like other nerves get stuck in between the bones and muscles and other things that don't belong in between your bones. Because as your ligaments and tendons stretch because they're not used to being used, it opens up gaps between your bones. So, and I don't say this just because, I'm not saying this just to go on some tangent. This is actually extremely important physics, and it's not well known even to athletes. How many of you have played a sport before? Played a sport in high school? Okay, how many of you stretched out for a sport? How many coaches encourage that? Why? It's like the dumbest thing anybody can do. Stretching is so bad for your body. And they do it all the time. Why do we do it? Stretching literally is just stretching out tendons and ligaments. Why does that do anything for us? It doesn't stretch your muscles. Muscles don't really stretch. It stretches the tendons and the ligaments. The tendons and the ligaments, their whole purpose is to keep things together. If you stretch them apart, what are you doing? Well, you're creating gaps between your bones. What's the worst thing you could do for a knee? Create a gap in it, right? If you create a gap in your knee, you are going to blow out your knee every time. And that's exactly what happens with every knee injury. People are stretching out, and this is proven science at this point. This is if you go into professional athletics or even high level like collegiate athletics, UNL for example. UNL was terrible at this for years. They were doing all kinds of stupid things with their athletes, and I had a friend that went there and just destroyed her life, literally. Like literally, she is a cripple because she was a high-end athlete at UNL. Because they were thinking in terms of, they were going to their coaches to do the science of sport instead of to their scientists. And they weren't involving that the coaches weren't listening to the scientists. And this was true everywhere, really. I mean, this is not uncommon everywhere. But now, players don't stretch. They don't do these weird things where they pull their leg up over their ear and their arm over their whatever. They do all these weird things because it's bad for you. What you really want to do is you want to warm up your body. You literally need warmth because warmth causes movement of fluids. The synovial fluids, which are all the things that lubricate your joints, that's what makes your joints feel good. It's not stretching them, it's lubricating them. Stretching them will do that because it warms them up a little bit, but it also does damage because it stretches them out. So they just say, if you're going to play basketball, just go play basketball, just don't go all out. Play just light and, just move around a little bit. Do some jumping, but light jumping. Do some this, some running, just some light running. Do things, they actually call it, dynamic stretching. You're stretching, it's not really stretching at all, really. It's dynamic warm-up, essentially. You just warm up and you'll be fine. And they found that injuries have gone down with this throughout all sports, and it comes from science. It's not from, this coach who just has been in the sport forever and just knows everything. Baloney. Most coaches now are actually taking science classes just to become a coach. There are many coaches out there that have PhDs in physiology and PhDs in physiomechanics and PhDs in all these things that are very sciencey nerdy because they're trying to be the best. They're trying to do the best thing for their athletes. Probably one of the best examples of this is my basketball team, which is the Golden State Warriors. The Golden State Warriors have like 9 PhDs on staff, and all they do is sports science. And they're in there. They have their practice facility has like 1,000 cameras, not an exaggeration. 1,000 cameras where they're just taking pictures of the athletes from every direction, high-speed film, high-quality video. And all they're doing is they're looking at the mechanics of the players. So when they get the video in, they have these computers that actually break down the movement of each player and the movement of their knees and everything else. And if they're an injured player, they're looking for specific things. If they're a healthy player, they're looking for specific things. If they're trying to fix Steph Curry's step back shot or whatever, step back three or whatever, they can slow it down. They can look at the mechanics of it and they look at the science of it. And then they have all kinds of other sensors. They're always having their players breathe into things for the physiologists or the biochemists or whatever. They're having their players undergo MRIs for like no reason, just because they want to know more about what's going on in their body to make sure that they understand things, And just tons and tons of things. They're wearing sensors. Players are wearing sensors in their like shorts and stuff. They have these little pockets and they little Velcro inside it, put a little sensor in it, and they can track different things about what their body is doing. It's all about science. And Warriors aren't the only team doing this. NFL is famous for this. NFL is doing this constantly. Lots of sports are doing this constantly. So it's really quite cool. And this is one of the main reasons that sport over the past 10, 20 years has really just exploded with performance. All of the greatest things that have happened in sport, with a very, very few exceptions, have happened in the past 20 years. All of them. You have what's his name, who scored 105 points in one game back in the 50s or 60s. That's never going to happen again. It's possible, I suppose. But then you have a couple other guys that have done just so amazing. A couple other sports athletes have just done super amazing things that almost all the rest of them have in the past 20 years. Katie Ledecky is anybody know who Katie Ledecky is? Katie Ledecky is a swimmer. She is the nerdiest scientific swimmer. But she is just blowing every record out of the water. She can swim 100-meter freestyle with the same time 100 times in a row. And that time is faster than most people can do it once. And she can do it 100 times without stopping. 100 times she can get the same time. And then she comes in the race like 10 minutes before the next. She'll swim a mile. She'll swim 1,600 meters, and she's like, oh, no big deal. She gets out of the water. She's like, not even breathing. She's like, you gotta be kidding me. That is so hard to do. I can't even do 500 meters. And I was a swimmer. 500 meters killed me. But it's, so much about science, so much about understanding what's going on. And physics has become a huge part of that because so much of it is about force and energy. Let's look at another classic example. The tension in a tightrope. So here you have a person with weight, their weight pushing down on this tightrope here, right? Well, all of this weight has to be counteracted by the rope. if the rope doesn't counteract this tightrope walker's weight, what happens to the tightrope? If the rope can't put enough force in there to keep them up, what are they going to do? They're going to fall, right? It's that simple. Newton says that force equals mass times acceleration. If the acceleration is 0, this tightrope walker stays where they are. If their acceleration is not 0, they accelerate, which means they fall, right? So this force plus these two forces has to equal 0, because it has to equal a mass times acceleration equals 0 thing. But these two forces here are pointing sideways. How can they counteract this one? Well, they're not pointing exactly sideways. They're pointing a little bit up and a little bit up, right? In order for them to add together to give you this downward, this much, this much force to counteract this much force upward, they have to actually stretch out quite a bit. They have to be quite long. In other words, the tension has to be really tight. It's the same as the tendon in your arm, right? There's something going on here, which we'll learn about later, that causes this huge tension, even though this is only a 10-pound arm. And that's probably a little bit more, but a 10-pound arm would give you about 100 pounds of force on that tendon, 100 pounds of tension. So you think this one, this could be 100 pounds of weight, and this might be 500 newtons or 500 pounds of tension. It might be a lot more tension, or maybe even 1,000 pounds of tension. So how do we do this? Well, they say there's a 5-degree sag here, and so we're going to create components for this tension vector. There's one going to the left and one going to the right, and each one of them has a horizontal component, T sub x, and another one has, each one of them has a vertical component, T sub y. There's a left y and there's a right y, and T left y plus T right y has to equal the weight of this weight of the tightrope walker, or they're going to fall, right? So this is what the free body diagram looks like. The horizontal components, they're just going to be canceled. They're just going to cancel each other out. This one's going to be equal to this one, whatever. But what do these have to be? And that's what they're going to calculate here. The net force in the x direction is just this one here equals this one here equals the negative of that one there. So when you add them together, they add to be 0, and that's fine. So that means the T left x equals T right x. With the cosine of 5 degrees, we can actually use this T left x over x is the definition of the cosine, because T left x is this adjacent side, T left is the hypotenuse, right? So we can use the definition of the cosine here with the 5-degree angle that we know to actually solve this equation for, actually we're not solving it for anything. We're just solving this, we're solving this equation for T left x, I guess. And that's just standard. And they do it for both. They do it for T left x and T right x. And then they're going to set them equal to each other, because they have to be equal to each other. And that all that really gives is just, it proves that they're equal to each other. That's fine. So all they've done there is something that's, we call that a, what do we call it in physics? We have a word for that, I can't remember what it is. But anyway, but when we're doing the other one, for the y one, the one that goes up, the T left y and the T right y, we calculate those, we get the equations for those, and we also know that those are going to be about equal, but what we really want to do is we want to put them together in the equation for weight, with weight. All the forces in the y direction are T left y plus T right y. Those are the two that are going up, so they're positive. But the one that's going down is negative, so we subtract off the weight, and that has to equal 0 because we don't want our rope walker to fall. So when we put these into this equation and then we substitute t times sine of 5 degrees in for this one, and t times sine of 5 degrees in for this one, then what we get in here is this equation. T sine 5 plus t sine 5 minus weight equals 0. That's 2 times t times sine of 5 degrees minus weight equals 0. And then we get a relationship between the tension and the weight. Tension equals weight divided by 2 times sine of 5 degrees. Well, the weight is just the mass times the gravity. We know that. We plug it in. 3,900 newtons. We have a 70 kilogram, in other words, a 700 Newton tightrope walker, and the tension on the ropes is 3,900 newtons. Right? Almost 6 times greater tension than the weight of the tightrope walker. So here's another kind of tightrope. You have a car stuck in the mud. How do you get it out? Most people are just going to hook a chain or a rope onto the front of this and get their big old SUV and pull it out, right? But there's an easier way if you don't have an SUV, but you do have something like a tree. You can put a tight rope in between the tree and the car. But instead of pulling it straight out, do what the tightrope walker does. The tightrope walker stands on the rope this way and creates this huge tension along the rope, right? What we're going to do is we're going to put the car in there and we're going to push on the rope sideways, as if we're a sideways tightrope walker. Or you could even stand on it. If it's high enough off the ground and tight enough, you could stand on it, use your weight to push it down. But what that's going to do is it's going to create a huge tension between the rope in the car and the rope in the tree. A small force here will create a huge tension here for the same reason that the tightrope walker creates a huge tension in the rope. Right? Because you're pushing sideways instead of pulling this way. And you can pull a car out really easily this way. So next time you get a car stuck in the mud, try it out. We have a picture of Golden Gate Bridge after all. If you're ever that close to the Golden Gate Bridge, you're ever actually walking across the Golden Gate Bridge, you should probably go down the coast. You're going to go down south from the Golden Gate Bridge, past the, going to go past the Golden Gate Park, past the Presidio, and then you got to go around the bottom of the San Francisco harbor there, and you got to go see. You got to go see the Exploratorium. It's the greatest hands-on science museum ever. We've got so many cool experiments you can do in this museum. Super fun. Anyway, okay, so moving on. In these books, in all physics books, they always get you to a point where they want to tell you how to do the problems, how to step through problems, and that's what this section is. How do we get through, what kind of strategy do we need to use when we're doing problems? So they say identify the physical principles involved. I like to say the first step is always to draw a picture and write down the things you know, which is what they mean here by identify the physical principles involved. Draw a picture and see if you can understand what they're talking about. Label everything that they tell you. If they tell you the weight of an object, if they tell you the mass of an object, if they tell you whatever, distance between two objects, if they tell you the time that something takes, write all that down and use vectors to represent things that vectors can represent. And do all these things so that you can have a visual representation of what you're actually doing. Tarzan with his loincloth. I always imagined Tarzan wouldn't have a loincloth. Why would he have a loincloth? He was raised by apes. He would just want to put more hair on his body. I don't know. Anyway. In the Tarzan movie I like to watch, it's Christopher Lambert. Yeah, that's a good one. I can't remember if he has a loincloth in that one. I think he probably does. But in that one, he's like a bodybuilder, so he has absolutely no hair on his body. Anyway. Okay, what was where are we at here? A little sidetrack. Okay, here we go. So Tarzan. No, that I know what that was making me think. Have you guys seen the new Marvel movie, the new Endgame one? Have you seen that movie? Oh. Have you seen any of the Marvel movies? Like if you haven't seen any of them, it's not funny. But my kids love those movies, so they took me to see that one. In all these movies, they have this bodybuilder who, that's what I was reminded of when I saw the Tarzan movie. And they have this bodybuilder guy who plays Thor, and he's like, I don't know what his name is, he's like some famous actor. But he's like super built and muscular and everything. But in that last movie, he's fat, like super fat, and it's real. Like it wasn't CGI. He actually went out and got fat for 6 months. And it's so hilarious. I loved it. It was awesome. He like comes out of his house and he's like beer belly and all dirty. It's so funny. Everybody at the theater is like, no! Too funny. Anyway, okay. The next thing you should do is to identify what you want to know and start listing things like equations, and especially to draw a free body diagram. Once you've drawn a picture like this, you need to identify the forces that are external to your system of interest, and you want to draw your free body diagram, and then start writing down equations. Essentially what you're writing down is Newton's second law in most cases. But you also might have to write down some kinematic equations. Maybe you have to figure out the acceleration from a change in velocity. But you should write down equations that you think you might need in step 2. Then, once you've drawn a picture, figured out your free body diagram, the things that you're trying to find out, the things you're trying to solve for, and you've written down some equations that you think you'll use, then that is when you start to actually solve the problem, do the math. Now, I would recommend highly that every time you do a problem in physics, you don't plug numbers in until the end. Create a formula. Solve all the equations that we have first for the answer, and then plug in your answer. Plug in your numbers and get your answer. And then you'll be much happier. And here are your equations here's an example. Not any equation, but here's an example of equations you might write down for a system that's accelerating in the horizontal direction, but it's not accelerating in the vertical direction. So this is like a race car that's moving down the track, and that's your x direction, but it's not going up and down at all, so it has no acceleration in the y direction, right? For the net force in the x direction is going to equal the mass times the acceleration in the x direction. The net force in the y direction is just going to equal 0 because it's not going up and down. That can still be useful. An equation that's equal to 0 can be very useful still, because you might have 4 different forces over here, or 2 different forces, or whatever, and you might be able to solve for one of them by setting them equal to 0 and solving for that one force. In any case, you should write down those equations because you might need them to solve your problems. So here is another great example. This is another classic example, boats pushing on boats. So you have a tugboat pushing this way, and a tugboat pushing this way on this big old barge. The acceleration is off in this direction somewhere. How do we know which direction it's in? Well, we know from the sum of all the forces. That's actually not a problem. That's not something they give you in the equation. Actually. This is an answer, not something that's given. I don't like that they put it there, but they do. But in this case, you have 2 forces, force in the x, force in the y, from these 2 different boats. But you also have a drag force. There's drag or water resistance, essentially, from the boat moving through the water. So you have this drag force in this direction. And the net force, the total force, minus the drag force, or the force, the force applied by the boats, which is this big one here, minus the drag force equals the total net force, which is this smaller arrow pushing up in this direction. So they've drawn all their forces here. They've created a free body diagram here. Then they've even actually broken down the applied force into 2 components: the x component of the applied force, which is just this, and the y component of the applied force, which is just this. It's actually, they've just handed it to you here. This is a great problem for an exam, because if you don't understand it, you'll probably start going crazy. There's so many forces. But if you do understand it, you just know this is your x component, this is your y component, and that creates your total push. But then you have to subtract off a little bit of the drag force. And they tell you what the drag force is. No, they don't. They tell you the observed acceleration. So they're telling you the total acceleration, and all these forces, the applied force minus the drag force has to equal, the applied force minus the drag force has to equal that net force, and that net force has to equal mass times acceleration. So they do that right here. The applied force equals force x plus force y. They actually calculate the applied force here by using Pythagorean's theorem, fx squared plus fy squared square root thing. They calculate the angle of that applied force so that they can know which direction it's going. Then the net force, which is the applied force minus the drag force, equals the mass times acceleration. That's what they're doing right here. And then the acceleration is given. They told us the acceleration, and so we solve this for the drag force. We plug in all the numbers, and we can calculate that drag force from that equation. But it's important that you know that the net force with the correct sign, the applied force is positive, the drag force is going to be negative because it's going in the opposite direction. Can equal the mass times acceleration. Here's another classic physics problem that we love to give, where you have something hanging, some kind of mass hanging from two cables that are at different angles here. So this looks like a fairly complex force picture. We've got the weight of the light down, we've got the tension of the first rope, the tension of the second rope. Each one of those ropes has these components to it. In the free body diagram is simple. It's just weight down and two tensions up to the left and up to the right. When you break it down into a free body diagram of all the forces, all the force components, there's two Y tensions from each rope. There's two X tensions from each rope, and then there's the weight that is just a Y. So in other words, all these forces in this direction have to add to be zero, because stoplights aren't meant to be accelerating. So all the forces have to add to be zero in both directions. So these two forces added to this force, which will amount to tension 1y plus tension 2y minus weight, has to equal zero. And in this direction, tension 2x minus tension 1x has to equal zero. And that gives us two equations. Tension 2x minus tension 1x equals zero. That just tells us that those two tensions are equal. And then tension 1y plus tension 2y minus weight equals zero. There's our second equation. That tells us this. Now we have two equations and two things that we don't know. We don't know tension 1, we don't know tension 2. And we have two equations, this equation and this equation. This equation they actually solve by using the angles. T1x is equal to T1 cosine 30. T2x is equal to T2 cosine 45 because of their angles. And that gives an interesting thing here. Because these two have different angles, and and we solve this equation that we've created here in the x direction, it gives us a relationship. It tells us that T1 times 1.225 equals T2. So it's given us a relationship. This next equation, T1 plus T2y minus w equals 0, doesn't really give us, it gives us kind of a mess because we don't know T1, we don't know T2, and we don't know the weight. Or do we know the weight? Maybe we do. We probably do know the weight, but still, this still has two things we don't know, and this one has two things we don't know. But because in this one we've been able to create a relationship for T1 and T2, we can actually plug this one in to this one. And that's what they do right here. Instead of T2 right here, they plug in this right here, which is equal to T2, right? So they plug in 1.225 T1 instead of T2. And then the second equation has nothing but T1 in it. Now you've probably seen that in college algebra before, where you have two equations, two unknowns. We solve one equation for one variable, plug it into the other one, right? Call that solving by substitution. And we do that quite a bit in physics, quite a lot. Once you've solved this equation for T1, you'll get an answer, 108 newtons. Then you can plug it back into either one of these equations above and get T2. The bathroom skill in the elevator. Instant weight loss program. This one confuses a lot of people. We try to give examples of the things that can be quite confusing to students, and so this is one of them. This one confuses people mostly because we're talking about an elevator accelerating up or down, one or the other, but we're talking about the weight that you read on the scale. Weight that you read on the scale is not acceleration, right? The weight that you read on the scale is mass times acceleration. So you have to think of it in those terms. So the free body diagram has the weight of the person on the scale. So the person pushes downward on the scale. It's this one. So this is the weight of the person pushing downward on the scale. But the scale pushes upward on the person. So the force of the scale is upward. And the object of this one is we have this 75 kilogram man. Calculate the scale reading if the elevator accelerates upward or if the elevator moves upward at constant speed, right? So if the elevator is accelerating upward at a rate of 1.2 meters per second squared, that's going to change the scale reading somewhat. How is it going to change it? What's that going to do? Let's take a look at what they're doing here. First, they take the net force equals mass times acceleration, just writing down Newton's second law. This is, surprisingly enough, something very few students get right. And I'm not talking about getting the equation right, I'm talking about just writing it down. That is the right thing to do. Just start writing things down, and oftentimes things come to your mind, you're like, oh, I know what to do with that. Oh, I know this should go in there. But if you never write anything down, especially on a complex problem, you're not going to get anywhere. So just write something down. And this is the very simplest thing to write down in physics. Force net equals mass times acceleration. What does force net mean? It means add all the forces in a single direction together, and that should equal the mass times acceleration in that direction. In this case, the force of the force that the person is pushing on the scale minus their weight is the net force. So the force on the scale minus the weight has to equal the mass of the person times the acceleration of the person, right? So we're going to solve this now for force of scale equals mass times acceleration plus weight here. So in this case, we've not written anything down, we've just solved it for the force on the scale, right? The weight is the mass of the person times gravity, and that's great. But this has an acceleration in it that is unknown, right? And that acceleration is going to be the acceleration of the elevator, which is actually known. We've written it down as if it's some kind of variable, but they've told us what the acceleration of the elevator is. Make sure we get the sign right. We've already said that down is, because our weight here was negative, that's assuming that weight that going down is negative. And this, in this case, the bathroom scale accelerates up. So our acceleration here needs to be positive, right? So when we plug in our acceleration in here, it needs to be positive. Mass of the person, let's see, that's not there we go. The mass of the person times the acceleration of the scale they're standing on, or the whole elevator, right, is 75 times 1.2. This is essentially the acceleration of the person, because the person is our system of interest, right? So it's acceleration of the person, but because the person is in the elevator, their acceleration is the same as the elevator. So acceleration of the person times the mass of the person, 75 times 1.2 meters per second squared. Then this is just the weight of the person, 75 times 9.8 meters per second squared. And then you get this 825 Newton force on the scale, which is actually more than they would weigh, which you'd expect. When the elevator goes up, the scale also goes up, right? When it accelerates up, the scale goes up. Now the same equation, force on the scale equals mass times acceleration plus weight. That will work also for the part B, except there's one thing that's different. There is no acceleration in part B. In part B, the elevator is just moving up at a constant velocity. It's moving, but there's no acceleration. So essentially it becomes force on the scale equals the weight. So the weight of the person is the force on the scale, and they go through a long rigmarole to show that, but it just ends up being 735 newtons, which it would have been if the elevator was stopped also, right? So constant velocity, no velocity, gives you the same reading on the scale. acceleration will change the reading on the scale. Acceleration upward will increase the reading on the scale. Acceleration downward will decrease the reading on the scale. And therefore, that's a boring word. Excuse me. All right, so that takes us all the way through chapter 4, Newton's laws of motion. We've already talked about the 4 basic forces, so we're done with that. So, I guess then that takes us to, does anybody have any questions on chapter 4 homework specifically? I know that there were a lot of questions on my open math, but like I said, I didn't read through them yet, so I don't know if they were on chapter 3 or chapter 4. But has anybody started chapter 4 and come across something they have a question on? 22. So there's 28 problems.
So I got the net force, but when I did the acceleration.
Okay, net force on the box of all the forces acting are shown below. So it's 20 newtons up, 31 newtons up. So the net force is going to be 51 newtons, right? The direction will be up, right? What are those boxes? What are those things for? Okay, now that you found the net force, you did find the acceleration on the box. So how do we do that? Newton's law says what? So acceleration equals force net over mass. In our case, in this problem, 51 newtons. And that's my box's mass. 63 kilograms. So we got 51 newtons over 63 kilograms. That's going to be about 0.87 meters per second squared, I'm going to guess. Let's calculate, see how close I am. I think I'm off by quite a bit, actually. 51 divided by 63. Yeah, I'm off by quite a bit. It's only about 81. Or 8.809 meters per second squared. So let's go and see if that's true. Test it with my numbers and see if it works. Now in my open math, I generally try to enter 3 digits just because it tends to like that. And the acceleration would be that. Oh, no direction. Let's see. So I'm going to submit that really quick and see what happens. See if it's. So it gave me the force right. It gave me the acceleration right. I didn't get the units right because I didn't write them in. So it'll be meters per second. Use a little code here. Squared like that. So my guess would be is that if you use that same formula that I did, that maybe you should put in another digit and see if that's true. And if it takes off any points because you didn't put in enough digits, just send me an email real quick and say, can I have credit for this even though I didn't, because I didn't put in the right number of digits, and I'll give you the full credit. That's totally fine. But if it's still not giving you the right answer, definitely email me again. But that seems to be correct here. What's the answer going to be here? If the object is moving down and then the acceleration happens, what's going to happen to this object? Continue to sit there like a rock? Well, it's not sitting like a rock anyway, right? It's already moving down. Should continue to travel right, but will slow down. It's not traveling right. So we can get rid of the next three also. Begin to travel right and speed up? No, because the force is up, right? If it's going down and you have a force upward on it, it's certainly not going to go right. The left ones we can throw out, the left ones we can throw out some more. Continue to travel up. Well, it wasn't traveling up, so we can throw away the next three. Begin to travel up and speed up. So if it's moving down to begin with and then you have an upward force, will it do that? Will it begin to travel up? Right after you start applying? No, not necessarily. Don't just go immediately from traveling down to traveling up. What do you have to do down? What do you have to do first? If you're moving in one direction and you want to go the other direction, what do you got to do first? You got to slow down. There's no such thing as immediate turnaround, right? Some people say that James Harden's step back is immediate. It's pretty close. But anyway, you have to slow down, right? So we're going to be continue to travel down, but we'll slow down, continue to travel down, but we'll speed up. Continue to travel down at a constant velocity. Begin to travel down and speed up. Continue to travel down, but we'll slow down. I think that's what's going to happen right after. So the upward force will slow down the downward motion when it starts to be applied, right? Eventually, if it's applied for long enough, we may even stop it. And then what would happen after that if that force is still being applied? It would go the other direction. Did you guys see that in the lab yesterday with the fan carts? It wasn't up and down, side to side. Yay! Any other questions you want to look at in the homework in particular? Should we pick one at random? We'll play physics roulette. Blink. Classic. You ran out of gas. Your car is moving to the right, coasting to a stop. Identify the appropriate free body diagram for this situation. Let's make it a quiz. Get a piece of paper. My quizzes are really easy usually. If you get the question right, you get 10 points. Usually there's only one or two questions on it. If you get the question wrong, you lose a point. So you get 9 out of 10. The quizzes aren't intended to stress you out or test your knowledge of anything. Quizzes are intended to make you think and then help you to understand help you to explain and justify your answers. So pick an answer, A, B, C, D, or E. Put your name on it and the date. Everybody done? All right, now, anybody want to share their answer? Class?
I choose B.
B. Okay. Justify your answer. Tell us why you chose B.
gravity eats out one car.
Which just happens when you're on Earth, right?
Yeah. And then the F1 that's from the car, or the friction from the car.
Yep.
And then the friction would be from the ground and the car coming to the stop.
Okay, so the friction we know is there too because it's coasting to a stop. Any other forces? Anybody do another one?
I put D, but I'm pretty sure D is right, and I forgot that gas was
Yeah, so you put D, you said?
Yeah, but I forgot the friction force on that.
Yeah, so even before the car runs out of gas, the friction is there. Before the car runs out of gas and it's still moving, with its engine pushing it, this would be correct, right? This one would only be correct if there's no friction or if it's not moving, because friction doesn't happen if it's not moving, right? This one, and this one would only happen, this one is not correct if it's moving forward. This one is correct if it's moving forward. Why is this one correct and this one not? Why is this, well, okay, correction. This would be moving forward at a constant speed. This one would be accelerating forward. So getting faster and faster, faster forward. Why? What's the difference between these two? What about them?
On E, the friction vector is shorter than the applied.
So here the applied force is bigger than the friction. Here the applied force is just enough to be canceling out friction, which is what you're doing when you're on the freeway and you're holding constant at 85 miles an hour. In the 75. No, what you're doing when you're holding constant at speed is you're just giving your car enough, you're giving enough drive from the engine just to overcome the friction in the wheels. And that's a lot of friction. Take your foot off the gas. And it's not just friction of the wheels, friction of the air too. It's a lot of friction. Take your foot off the gas and you're down to 50 in 5 seconds. You know, maybe 10 seconds max, depending on your car. But yeah, there's a lot of friction to overcome. So the correct answer is B. If you did put B, go ahead and give yourself 10 points. If you put something else, give yourself 9 points, and we'll turn it in. Write it out. Write your score on there for me. Turn it in. For those of you watching this later, just send me an email with your answer. Make sure that you actually participated in the quiz before we do it. And we'll turn those in. Get a copy. I like to do a quiz every once in a while just to kind of keep us awake. Physics in the summer can be a sleepy business. All right, so let's take a look at our calendar. It gets kind of annoying and crazy during the summer because because our schedule is so kind of weird. People ask me, why do you only teach 3 days a week and why do you teach in the afternoon? Well, I teach in the afternoon because in the summer I like to work outside a lot. I do a lot of gardening. I do a lot of working on my house addition. I do a lot of work outside just in general because I like to be outside in the summer. It's nice out. But in the afternoon it sucks. So I do class in the afternoon where it's air conditioned. I get up in the morning and I work all morning and I get all sweaty and dirty and then I take a shower and put on some clean clothes and come to class for 3 hours and I don't feel terrible working through the hot afternoon. The other reason that I like to do it 3 days, long hours, is for work schedules. I found that works better for most people. To be able to work around that, it's easier to get a schedule where you're working 8 hours one day and 4 hours another or something like that. It's just worked better for most students. So, but it does create a little craziness as far as going through chapters and stuff like that. So, since today we've got about an hour and 15 minutes left, we do have time to start chapter 5, but we certainly will not finish it today. So we'll probably move chapter 5 homework to next Tuesday, hoping that we can finish it next Monday if we start it today. But of course, chapter 4 is certainly not done. We want to move that off a little bit, but not too much because we don't want you to put it off too long because we want you to start chapter 5 as well. Eventually, towards the end of the semester, well, probably in a couple of weeks, we'll probably be doing, we'll probably have a little bit less crazy schedule, I don't know, whatever. But summertime is always just kind of crazy no matter what happens. But this puts us in a position where we might be able to do chapter 1 through 5 exam next Friday, which would be good. Our schedule, we're going to try to get through all 16 chapters. We don't always do it in the summer. So if we have chapter 5 due Tuesday, that means chapter 6 can probably do maybe Monday. Chapter 7 we can maybe put in here somewhere. I'm just throwing this stuff up to see how we're doing as far as time for the class. See if we'll be able to fit things in here. Let's see what month. So this would be August 1st. When does the class end? Does anybody know? August 1st? Sounds about right. Okay, so it's August 1st, then we gotta fit in a few more things here. Chapter 11, somewhere here maybe. And then chapter 10, exam, chapter 10. So we can probably get this done. You know, essentially it's about 1.5 chapters a week is what we're trying to fit in over the summer. And I think we're on pace to do that. So we're in good shape. Maybe more weeks to have. Any more chapters? Here's the 12. 12. Where'd my other chapters go? Oh, I bet you that I didn't have those chapters done yet. When I taught this last. Yeah, so I'll have to put the new chapters in, the new assignments in. The new assignments for this class. But final exam, essentially, we'll put in this week. We'll try to get in 11, 12, 13, 14, 15. We can probably get in most of all the chapters. All right, in good shape. Let's go ahead and look a little bit at chapter 5 and see what it's got in store for us. So again, this is more of Newton's second law. We're going to mostly be studying friction, but towards the end here we'll study what we call elasticity, stress, and strain. So we'll start off with friction. So simply put, friction opposes relative motion between objects. Objects that are in contact with each other in any way are going to have friction between them. Why? Well, it's really quite simple. If you zoom in on an object, you'll notice that the object surface is rough. It becomes very obvious with technology that we have today. Here is, we call a scanning electron microscope uses electron beams to look at surfaces. So let's look at this. This one is a piece of glass. So you see, here we go. So there's your Apple iPad glass right there. If you know your iPad or iPod or iPhone or Samsung or whatever, they have really high quality glass on them. Really high quality, much higher quality glass than was even available when I was a kid. They've made these things so smooth because they want them to be super easy to run your finger over. That's really what it comes down to. They want them to be super smooth for that purpose. And you know, a lot of people like to put these covers on them. If you put a cover on it that's a poor quality, it totally slows down your finger. It makes it really uncomfortable to use. It just doesn't work right. And so it's actually just best to just leave the glass open, I think. Oh, a really cool thing happened recently. So being a nerd, this is a little bit of an aside, but it's quite relevant. Being quite the nerd, I've always watched movies like Star Trek and things like this, and I'm a big fan, I still am. When I'm grading papers, I'm always listening to old sci-fi movies and sci-fi TV shows and new ones. But there was one Star Trek movie where the people in Star Trek went back in time. Of course, that's a very common theme in science fiction movies.
and they go back in time to the 80s, which of course was when I watched this movie because it's when they made this movie. And they go back to San Francisco, which is where I was living at the time because I was a kid. And they go and visit the USS Enterprise, which was an actual aircraft carrier that was stationed in San Francisco when I was a kid. I've actually been on it. It's still there, actually, I think. It's a museum now, but actually, it's the Kitty Hawk. I don't remember which one. It's not that one. It's a different one. Doesn't matter. Anyway, when they're there, they have no money because they're from Star Trek, and Star Trek doesn't use money. They're beyond that or something. But they need materials because they're trying to bring these whales back to the future to save the world or something. It's very politically incorrect. But they have no money, so they're talking to this person about buying some plexiglass or polycarbonate glass to make some big tanks inside their spaceship. And why they needed clear tanks, I don't think why not just make the walls out of steel? That'll still hold water. But anyway, they had to make them clear for the movie set. So they're trying to get this polycarbonate material from this plexiglass, and they have no money. He says, well, I'm not going to give it to you for free. This is hundreds of thousands of dollars worth of glass. And they said, we'll give you a formula for clear aluminum, for see-through aluminum, which is one of the materials that Star Trek supposedly uses. They've actually figured out how to make it now. It's really kind of cool. They actually mix aluminum powder with some other chemical powders, essentially, and then they bake it and they make a clear aluminum. They make an aluminum, and it has to be polished to be clear. But it's really super cool. I mean, I gotta see this thing. So let's do this. This is a very recent thing that's happened. And the really funny thing is, nobody would have thought of this. Nobody. If Star Trek hadn't come up with this idea, this totally off-the-wall idea. Of course, nobody would have come up with doors that open themselves without Star Trek. Star Trek was they were the first people to come up with this idea that if you just walk up to a door, it just opens itself. And in the original movies and the original TV shows, they just had a guy sitting behind the door with a lever, and they had this little thing that made a sound that would, when they opened the door. It was just a guy that did it. Now we have doors that open themselves all the time, right? But this is just amazing. So clear aluminum, it's called aluminum oxynitride, is what it's called, aluminum oxynitride, transparent aluminum. And there's this great, right here. They did this last year, a year and a half ago. What the heck? Oh, no. Oops.
Transparent aluminum was once pure science fiction, a technical term used in a Star Trek movie from the 80s. In the movie Star Trek 4, The Voyage Home, Captain Kirk and his team go back in time to acquire 2 whales from the past and transport them back to the future. Scotty needed some materials to make a holding.
That was the cutting-edge computer of the time, the Macintosh Plus. My father had one.
Tank for whales on the ship, but had no money to pay for the materials. So Scotty uses his knowledge of 23rd century technology and the manufacturer's computer, and he programs in how to make the transparent aluminum molecule.
Transparent aluminum?
Which could allow the manufacturer to create aquarium tank walls 1 inch thick instead of the traditional 6 inches thick. Now the words transparent aluminum sounds like it's 100% pure see-through metal, but in actual fact it's a mix of aluminum, oxygen and nitrogen in the form of white powder. The powder then gets packed into a mould in the shape of the desired part. The mould is then subjected to extreme pressure and then heated to 2000 degrees for several days. The surface of the final part comes out cloudy and has to be mechanically polished to make it optically clear. It starts to sound less impressive and less sciencey fiction when you hear how it's made, but the end result is still very impressive, as transparent aluminum, which is also known as ALON, can be turned into very damage-resistant glass and can be used to make highly bullet-resistant armour for military vehicles. Transparent aluminum armour is made of 3 layers, just like bullet-resistant glass, 2 panes of glass and a middle pane of polycarbonate. The main difference is a 50 caliber bullet can penetrate 6 inches of traditional bullet-resistant glass, but cannot get through about 1.5 inches of ALON armour, which means you can provide soldiers with far better protection on military vehicles for far less weight. ALON is being
Pretty impressive. It's actual transparent aluminum from a 1980s, almost 1970s. 1983 was like just barely after the 70s, essentially. It's just crazy. Anyway, back to what we were doing. A little bit of an aside there. So you have these surfaces here that are definitely rough, even though they look clear, and you can take the smoothest thing on Earth and look at it under a scanning electron microscope and find all kinds of just crazy things on it. Like this is super smooth glass that is specifically designed with these bumps in it, actually. But those bumps are so small. So here we go. So those bumps kind of get locked in with each other. You can kind of think of it as your knuckles getting locked in with each other, and as you try to move them along, they have to kind of move over the top of those bumps. And sometimes those bumps break off and make new bumps and whatever else, and you get dust building up in between things or whatever else. So I mean, this actually explains a lot of things. Rubber shoes are designed to fit into those bumps, right? You're designed to stick to those bumps. And specific shoes are designed to wick or to push water out of those bumps, like there are shoes designed to be used on boats. They use natural rubber because natural rubber has this natural affinity or natural unaffinity. What's the word for that? I can't remember. But anyway, it repels water very naturally. It's hydrophobic, as they call it. So you have that like gummy rubber on the bottom of them that pushes the water away from the shoe and sticks to the deck of the boat. They have special shoes that are actually push oil away really well, and those are often used in fast food restaurants where there's a lot of oil on the floors everywhere, right? So, but then there's also two kinds of friction between solid surfaces. So if you have two solid surfaces together, and let's take for example this remote control sitting here on top of this physics cheat sheet, which I still haven't sent to Brittany, which I need to do. Send me your address, Brittany. Also, Jacob, send me your address and I'll send you a physics cheat sheet you can use on homework and exams. But anyway, if you push on this remote, you'll notice that as you're pushing on it, it doesn't move. If you push on it just a little bit, it doesn't move, it doesn't move, it doesn't move. Keep pushing a little harder, and eventually it moves. You've all had this experience, especially if you push something heavy across like a carpet or a tile floor or something. Once you get it going, it's easier to keep it going. But starting it, maybe not so easy, right? So there are two kinds of friction. One of them, the friction that keeps something from moving, is called static friction. The friction that you use to keep something moving, or the friction that is there when you're keeping something moving, rather, is called kinetic friction. So kinetic meaning movement, and static meaning still, not moving, right? And they're actually calculated in the same way, except with static friction, the calculation tells you the maximum amount of friction that will be applied in that situation before you start moving it. So it can, if I push with 1 Newton against this, well, we have to push something bigger for 1 Newton. If I push with 1 Newton against my computer, it doesn't move at all. the amount of friction the computer's pushing back on you with is how much if I'm pushing with 1 Newton, according to Newton's third law? Equaling what? Equal and opposite, right? So what's the force it's pushing on me? If I'm pushing with 1, it's pushing with 1. If I'm pushing with 2 and it's still not moving, it's pushing with 2. If I'm pushing with 3, even if it is moving, actually, it's still pushing it back on me with the same amount. But if I push and push and push and push and push, and finally I can get this thing to move, right? That point at which it moves, let's say that's 9 newtons. That is the maximum amount of static friction between the table and the computer. So it can push with any number less than that, but it can't push with any more than that. And that's why it's shown with this less than or equal to symbol. Because the static friction between any two objects, the friction that holds them still, can be up to, but not greater than, this amount. So it has to be less than or equal to it. We don't really use it as in this form. We just use it as an equal sign to calculate the maximum friction, right? Because we just want to know where that threshold is. And then if you push with anything less than that, then the friction will be equal to however much you push, right? Up until that point. And then it will move. Once it starts moving, then the amount of friction that will be applied will be equal to mu times n. Now what is mu? Mu is a coefficient of friction that essentially tells you how much things stick together, how much of that roughness there is. And so it's different for every two objects. It's different for sandpaper on sandpaper than it is for sandpaper on plastic. So if you have a piece of sandpaper and a piece of sandpaper, and they're both particular, like 400 grade sandpaper, you're going to get a particular coefficient of friction, static friction, and kinetic friction. And the mu's will have to be measured for those. But if you put Teflon against 400 grade sandpaper, it's going to be a different coefficient of friction. And so essentially you just have to measure for every new object you do. It's kind of annoying, but that's just the way it is. So here is a table of some fairly common coefficients of friction. Rubber on dry concrete, tires on concrete, has a static coefficient of 1 and a kinetic coefficient of 0.7. So this is essentially for a tire that's not moving or a tire that's rolling. A tire that's rolling on concrete isn't actually moving relative to concrete, is it? What does moving mean? Moving means that the two surfaces are sliding past each other. When you're rolling down the road, are your wheels sliding past the concrete? No, they're just kind of rolling on it. When they're sliding, that's when you hit the brakes really hard and your car skids. That's sliding, right? Or you turn a corner really hard and you wipe out, right? That's sliding. So the static friction is higher than the kinetic friction. That's why you want to keep your wheels rolling all the time. That's why we have anti-lock brakes. Anti-lock brakes slow the wheel down, but then they let it roll, and then they slow it, and then they let it roll. They don't allow the wheel to skid very much, because you'll be able to stop better if your wheels are not skidding, right? That's why we have anti-lock brakes. Rubber on wet concrete, you can see it goes down, that's expected. Wood on wood, pretty low, 0.5, 0.3. Kinetic friction, and see the static friction is higher most of the time, because getting things to start sliding is harder than keeping them sliding, right? Waxed wood on wet snow, that's skis, right? So skis sliding on snow, 0.14. Steel on steel, not so good, 0.6. Steel on steel, oiled, really good. Inside your engine, right? Oil, steel on steel. Teflon on steel, really good even without any oil. Bone lubricated by synovial fluid, really good, right? That's why you want your synovial fluids to be flowing when you work out. Shoes on wood, shoes on ice, ice on ice, steel on ice. That's why we wear ice skates. That's why I don't wear ice skates. I've worn ice skates 3 times. 3 knockouts. Not technical knockouts. Like I got knocked out 3 times. No more skating. I'm also not a roller skater. Anyway, so friction. 2 kinds of friction, both calculated the same way. For kinetic friction, it's just equal to mu sub k. Now notice here you have to use the mu sub k. This is the moving friction. This is the sitting still friction. You have to use the mu sub k for kinetic friction. You have to use the static friction, the mu sub s for static friction. This is called mu. It's a Greek letter. We use a lot of Greek letters in physics. So here they show the nice knees. Here you have an artificial knee replacement. Artificial knees are usually made of Teflon, and they're usually made of something kind of like Teflon and steel. So they're not nearly as, they're like 3 times less like loose, you could think of it as, less lubricated essentially, than bone with synovial fluid. And it's not even bone that your body works on, it's the cartilage, right? In between your bones. That stuff's even slippery, more slippery. But, so here's the skiing problem again. We've done this before. Now we want to actually measure, we want to actually calculate the coefficient of friction. We've done this problem before. We know how to calculate this force, or whatever force. We rotate our axis and everything else. But now, in place of that friction force, we put in mu k mg cosine 25 degrees. Why mu g mg cosine 25 degrees? Well, this is mu times n. What is n? The normal force. It's always the perpendicular force holding the two objects together, right? So in the case of the skier, the normal force is at this angle. We've got this 25-degree angle thing going on, right, for the normal force. So the kinetic friction is going to be mu k times mg times cosine 25. This is the mg force. This is mg cosine 25, right here, which happens to be the same length as this one. So that's why we know it's the mg cosine 25, because it's opposing the perpendicular component of the weight force. So we use the mg cosine 25 for our normal force with the mu k for waxed wood on snow or whatever it is in our table up here, but we're going to calculate it and see if it's the same. We solve this equation then. For mu k, it's the force of friction divided by the normal force, so it looks like this. And we plug in our numbers. Our force of friction divided by the mass of the skier times the gravitational constant times our mu k, not our mu k, our cosine 25 degrees. And that gives us our mu k, 0.082. Let's see if it's close. For waxed wood on wet snow. Oh yeah. Waxed wood on wet snow for mu k, 0.1, we said 0.086, right? So it's pretty close. A little bit lower, but not too bad. 0.082. So here's a great experiment. You have like the track that we were using the other day, whatever it is. I don't know what it is. But anyway, you have the track you're using the other day, and you put the car on it upside down, so it's sitting on its plastic. And then you lift the one end of the track until the car starts to slide. And then you measure the angle. And then you figure out from the mass of the car and the angle that it started sliding what the coefficient of static friction is for plastic on aluminum. It's the same kind of thing as the skier trick, or the skier problem. It turns out that the tangent of the angle is equal to mu k. So mg sine theta over mg cosine theta or sine theta over cosine theta. Tangent of that angle where the thing starts to slide is equal to, and that's exactly how they do these. That's exactly how they measure these constants. They essentially put a piece of material on a known material, and they lift it up and they let it slide, and then they put it on a different material, and let it slide, and let it slide. And whatever angle it slides at, they take the tangent of the angle, and that's the kinetic coefficient of friction. So, this is a kind of a cool thing. So what they're showing here is this is a type of microscope. It's called an atomic force microscope. How many of you have seen a record player before? Have you actually looked at the needle? So you have a record player has a. I actually have in my house. I have, I think, 2 or 3 record players, probably 3.
But I have two modern ones, and I have an old one called an Edison. They're actually not called record players. I can't remember what they're called, but anyway, it's not called a Victrola either. But this is what mine looks like. Almost exactly like that, actually. I want to see a picture. There we go. That's what mine looks like. And if you look on the inside, it's got this arm that's kind of on this this lever arm here. And if you look closely at the needle, this is what it looks like. That's actually not what mine looks like, but here's what mine looks like. So you've got this needle down here. This is actually a diamond on the tip here, and the idea here is this diamond sits down in the grooves on the record, right? And the grooves in the record have these little things in them that make that diamond vibrate. And the diamond is connected to a little lever arm, and the lever arm hits this little diaphragm, like a rubber balloon stretched over a pipe. And then the vibrations on that balloon, on that pipe, transmit themselves through this arm. This arm is hollow, and this arm gets bigger and bigger and bigger and resonates more and more with those sounds. And then it comes out the front, where this thing here is essentially your speaker. It magnifies that sound into this big bell thing. On the other ones, the ones called Victrolas, this one's a phonograph actually, but this one's a Victrola. This is the same thing. You have a hollow thing here, and the vibrations happening on that needle get bigger and bigger and bigger as this tube gets bigger and bigger and bigger. You hear the sound up the top. I'm fascinated with these old things, but really my wife is more fascinated with them. But anyway, the point is that we actually have a type of microscope that works on very similar principles, and they're called atomic force microscope. Actually, let's do an airframe diagram. That's not right. That's not right either. Okay, so in an atomic force microscope, what you have is you have this lever arm, and you have this small tip on it, but this tip is so much tinier. They've actually, the tips on these things are usually made using nanotechnology, where they create a tip that is literally just stacking atoms on top of each other. So that tip could be like 1/100th of a micron across or something, super tiny. Well, could be even smaller than that, nanometers across. Just maybe 10 atoms across at the tip. So that's super tiny, super tiny. And then they scan this thing across a surface that's super smooth. And what they're trying to do is they're trying to look what this surface looks like. So maybe they have a really smooth piece of gold, and they're trying to look they're trying to look at the gold atoms, maybe. Essentially trying to see how big the gold atoms are. And as they scan it across here, it's so tiny that the electrons on the end of those atoms on that tip actually come in really close contact with the atoms in the gold. And so they start bumping around, they start getting moved around. And as they move around, there's a laser that comes in here and bounces off this mirror and hits the end of this rod, and then every time this thing bumps up, it moves this laser back and forth, and this photodiode over here detects that movement, and it puts it into a computer and creates an image. And the image is not like a picture, it's just a representation of what's going on with this laser. But this is what you see in the end. The most famous picture of this is these gold pictures, taking pictures of actual gold atoms. So let's see. That's not gold, this is carbon. This was one of the more, this one right here actually. This was one of the more famous pictures where they were actually able to distinguish atom from atom from atom.
So they're actually detecting individual atoms. Each one of these represents an atom, and this shows that they have a very organized structure to them. And so it's really quite interesting. This very old concept using, and it's friction in the end. It's electrons bumping into other electrons, and that's what all friction is. So they're just using friction at a very, very tiny scale to actually see, quote unquote, it's not really seeing, but to actually detect individual atoms, which is just phenomenal. So cool stuff. And this one, like in this one, they're actually looking at, looks like maybe benzenes or something. But these are molecules that they've created this sheet of molecules, and they can actually see the shapes that the molecules form in this crystalline structure. So it's a crystalline. Oh, it looks like graphene. So this is essentially like pencil lead. So this is what pencil lead looks like. It looks like really up close with carbon atoms. Now we've always suspected that it looked like this, just from other things that we've done, other experiments we've done. We've never actually been able to look at the structure directly until just the past couple of decades, when atomic force microscopes have come into being. And this is what it would look like. This tip that only has just a few atoms down here is interacting with these atoms down here, and it actually creates a friction, and that friction creates that movement, that force in the arm, and the laser detects that force. Atomic force microscopes are becoming so easy to build and so affordable that I could almost buy one and have one here. We could look at atoms with it. So, becoming quite, they're such a simple machine. Okay, so let's see where we at as far as time. We've got time. I actually want to do some more. Let's do some more examples with the friction. Let's actually look at chapter 5 homework before we move on to anything else. So here's a very simple problem where we have Ernesto and Amanda apply 191.6 Newton force to a 6.8 kilogram car to accelerate across a horizontal surface at this rate. So they've told us force, mass, acceleration. Right? They want to know the net force and the frictional force. Right? So let's take a look. We have a cart. We have a pushing force, which I'm just going to call force. They usually call it force applied or something. They'll call it force applied. That's too much to write. I'm not going to do that. Just force. There's their pushing force. We also know that it's going to be accelerated. They tell us the acceleration. We know that, right? But there's a frictional force, which we don't know. And that always goes in the opposite direction of the movement. So I'm going to put a question mark on that one. And that's all we know so far. Oftentimes they write the frictional force down here on the wheels because that's often where the frictional force is, but doesn't really matter. If I draw my free body diagram, it's going to look like this. Of course, there is weight. Oh, the other thing that they tell us the mass of this thing. So we have mass times gravity pulling down on this. We have we have normal force pushing up on the earth, up on it from the earth. We have the force pushing forward, the applied force. Then we have a frictional force backwards. Right? Equations that might be useful. Well, I think the net force in every direction will be useful. So I'm just going to write it down in general. Net force equals mass times acceleration. Right? We have two different directions. We have the y direction and we have the x direction. I'm going to start with the y direction because it looks easier. The net force in the y direction. Well, what forces do we have in the y direction? We have the normal force, which is up, and we have mg, which is down, so that's minus mg. And that has to equal the mass of the cart times the acceleration of the cart in the y direction. What's the acceleration of the cart in the y direction? Is it falling through the floor? Is it flying off towards the roof? No, so what's the acceleration? 0. Right? So this means that n minus mg equals 0, which means that n equals mg, right? So now I know what my normal force is equal to. I know the mass of the cart, I know the gravitational constant. I know what the normal force is. It's equal to the weight of the cart, right? Which is normal in a situation where you have, you know, horizontal ground and no forces besides gravity in the up and down direction. If you just have the gravity and the normal force, there you go. If you're pushing it down, that's gonna change things. If you're lifting it up, that'll change things. But this is pretty normal for the normal force to be, not to use the word normal too many times. This is pretty regular for the normal force to be equal to the weight of an object. It happens quite often. In the x direction, we have the force net in the x direction equals, well, I have the pushing force that's off to the right, which I'm going to call my positive direction. And I have the frictional force off to the left, negative friction. Well, and that has to equal the mass of the cart times the acceleration of the cart. And this time, the acceleration of the cart, we know. That's something we know. Right? So this equation is going to give me force minus friction equals mass times acceleration. Well, there's two things in this part that I want to know. It wants to know the net force, that's part A, right? And it wants to know the frictional force, this is part B. And guess what? I know the mass times acceleration and I know the pushing force, so I can solve for part B first. I'm going to solve for this one first. And then once I know the frictional force, I'm first going to get the frictional force. Solve for part B. And then I'm going to do part A next. I'll plug in F into this top equation. I'll plug in the friction up here, subtract the friction from the pushing force, and get the total force, or the net force. So it's a little tricky because to get the first part, you have to know the second part. Right? So you do the second part first, and then do the first part. But it's not that hard. It's pretty simple. Oh. There's another way to do this problem, too. No, there isn't. Never mind. I thought there was another way because I thought they told us something else. But I don't think they did tell us something else. Let's go check, make sure. No, they didn't tell us. So if they told us what the wheels were made of and like where the friction was happening, essentially, then we could actually look up a coefficient of friction and calculate the friction that way too. But they didn't tell us that. But we could calculate the coefficient of friction from what we know, because we know the friction and we know the normal force. So if you know the friction and the normal force, then you can calculate the coefficient of friction. So we could calculate the coefficient. What if they asked us to calculate the coefficient of friction from what we know? If in this problem they were also asking us to calculate mu kinetic, the kinetic coefficient of friction, we could do that as well because we already know the normal force, which is something you have to know for that, and we've calculated the frictional force here. So once we know the frictional force equals mu, in this case kinetic, times the normal force. So we would take our normal force, which is equal to mg, and plug that in from the normal force. And then we were trying to find the mu sub k, and we would plug in our frictional force from here. So this one would come up here. This one would come all the way around to here. And then we would solve it for mu sub k. Mu sub k equals, right? Mu sub k is going to equal the frictional force divided by mg. And then we would be able to calculate the coefficient of friction in the bearings of the wheels or whatever, wherever that friction is happening, probably in the bearings of the wheels. So we could do that part from this information as well. One of the things that kind of drives students crazy with physics is sometimes they give you more information than you need. In this case, we were given enough information to solve for the normal force, but we didn't actually need it. If they'd asked us for the coefficient of friction, then we would need it. But they didn't. So be aware of that. Be aware that you won't always use everything that's given to you, or everything that you can figure out from looking at the problem. Sometimes there's just more information than needed. You just have to accept that. It's often. I mean, that's a happy situation to be in. It's way better than having less information than needed, right? That's pretty much what all science is today. I love scientists who say, we know this. The best one is probably climate change scientists. Climate change scientists have one of the hardest problems to do in the universe. The problem that they're like, so generally in science, when we're trying to solve a problem, you want to have more equations that are independent than you have variables. So then you always have enough equations to solve all variables. But it's almost never that way. It's almost always you have more variables than you have equations. And so you end up with all these things that you don't know, you have to guess at. You just have to make your best guess. In climate science, which is a really weird term, it's really just physics. But anyway, climate science is just a specific application of physics to the world. And in climate science, they have something like 37, probably more than that actually. Now, I mean, the 37 is a simplified version. If you really want to try to do climate science, it's probably like 10,037. But they have all these variables. Let's say they have 37 variables. The equations that they have to solve for those variables is like 18. So more than half of the things they need to know, they don't know. They have to use essentially guesswork to plug in answers for those. So they look at historical data and they look at models. They run these computer simulations and they say, well, that must be the answer because it looks right. I mean, that's literally what they do. And then they just put together something, and if it doesn't look good, they just kind of tweak it until it looks good. And then they say, we know this, which is ridiculous. If anybody did that in any other situation, they would get slapped. But scientists get away with it all the time. They get away with it in every science, from physics to chemistry to climate science to economics to everything else. I mean, and even in psychology, this happens all the time. We know this, we know this, we know this. Baloney, we don't know anything. We have estimations, we have projections, we have models, we can predict with some degree of certainty, but there's also, with every degree of certainty, there's a degree of uncertainty. And so many scientists are not willing to admit that to the world because we need to be smart. It's mysterious. Science is mysterious and nobody can understand what we're doing. That's a bunch of baloney. And the problem is that how much of our tax dollars go towards these sciences because we really think they know these things. You know? It's ridiculous. Billions of dollars were given to companies that have since gone belly up. And that's not have been, they're given every year. Billions of dollars go to companies and researchers every year to do these things that they know is going to change the world, and then it doesn't change the world. Their company goes bankrupt because they weren't able to create free energy for everybody or something, and then, or they weren't able to stop climate change because they were going to build. This is my favorite one is Nissan. We gave Nissan as a company out of Japan, right? The United States government gave money to Nissan to make electric cars to save the world. No, it wasn't Nissan. Sorry, it was in Sweden. It was in Saab. It was Saab. It was a Swedish company, car company, Saab. We gave like $5 billion to a Swedish company to change the world to make electric cars. American tax dollars, billions of them, to a Swedish company. They do not have an electric car today. This was done in 2008, and they completely shut down that program and bankrupted. Saab still makes cars, but they don't make electric cars. And this is true of every electric car company, including General Motors, the American electric car company, that was literally saved from destruction by the federal government by giving them $100 billion or something crazy like this. You give them $100 billion and then said, but if you're going to take this money, you have to make electric cars and save our country. You know how many electric cars they make now? 0. Chevrolet does not make a single electric car anymore. The Chevrolet Volt is dead. They don't make them anymore. They're not ever going to make them again. The only car company that still makes electric cars in this country is Tesla. And they make them because they're luxury cars. They make them because they're quiet and they look cool. I think they were kind of goofy, but the first ones looked cool. But that's physics. That's science for you. Science does this all the time, where we tell people we know things to get money. Essentially, and it's unfortunate that this happens. It used to be that people would just give money to scientists because they knew scientists were doing good things, but now scientists have to justify what they do by saying we're going to change the world because we know everything. Well, we don't know everything. We don't hardly know anything, but we do change the world. We just don't know everything. We're just trying to figure it out. Be aware of that. You'll be, voting in your lives, and you'll be making policy changes. Maybe you'll even be in office someday, or maybe you'll be influenced by somebody who's in office someday and thinking that you need to vote one way and not another way or whatever else. Think about that. Anybody that says they know anything, they're full of it. Not just scientists. Anyway, there's nobody out there that knows everything, or even knows enough to say that they know everything about this, everything about that. It's baloney. One of the better arguments about that is religion. Scientists, many scientists, it's not as many as people think, it's about half. About 50% of scientists love to say that religion is, of course, absolutely ridiculous, because there's no way to prove that. In science, I only believe in things that I can prove. Really? Didn't I just get finished telling you that all these laws of Newton were not provable? They're just things that we observe over and over and over again, and so we assume them to be correct. And as soon as they are proven to not be correct, as soon as we observe them any other way, those laws go out the window. That's what all of science is based on. All of science is based on, well, it's that way all the time that we see it, so we just assume it's always going to be that way. But we actually know that it's not always been that way. That's actually been proven. We know that science has not always operated under these laws. There's actually proof. And so any scientist that says, well, science is based on fact, and religion is based on faith. Actually, science is based on faith. It's just a different kind of faith. You're just putting faith in things that you've seen before, and you just have faith that it's always going to happen that way. People who are religious, and 50% of scientists today are religious. People who believe in religion, they are basing their religion on personal experience, personal observations, and what they believe about those personal observations. It's not just blind. You don't just say, oh, somebody told me to believe in this. That's not true of religion. I mean, it's true in some cases, but that's true in science too in some cases. But most people that truly live their religion believe in it because of the things that they see, how it changes the world. They see that it changes themselves and their friends and their family, and they see that it changes the world. They believe in it, and it's a self-fulfilling prophecy. Of course, if you believe in something good and then you act on it, it's going to do something good. That's the great thing about religion. It is a self-fulfilling prophecy. No matter what brings you into it, it does great things. It can do some bad things too. It's done many bad things. But many wars have been fought over religion. But the point is that of all of this is when you're going off into the world, don't fall for that. Don't fall for that whole thing that somebody knows everything about something, or somebody is so smart that they just understand. It's baloney. Anybody who says that's a fool. There's no question. Or they're a liar. Or they're both. So, enough of that preaching. I think we can be done for today. That takes us through section 2. Section 3 we'll come back to because it's kind of a different subject. Come back to that on Monday. We'll be done for the week. Does anybody have any other questions on homework or anything else? I'll get on and answer your questions that you've emailed me today. And did anybody have questions that they emailed me today that were for chapter 3 that was already due? No, we're all done with chapter 3? If not, just make sure you tell me that. But we'll be seeing you on Monday. Have a good weekend. You're wearing a volleyball T-shirt. Do you play volleyball or just watch volleyball?
No, I got this in Minneapolis.
Do you want to learn to play volleyball?
I kind of already know how, but
Oh, but do you really know how? Then let me show you something that will explain to you what I mean. Do you play volleyball? No. So there's let's see here. I need to stop my recording.